Hello everyone and welcome back to this exciting world of CAM programming and CNC. I know you've all been holding your breath for this day to come. That's right, students, it's time to program the other side of the Geneva Drive.
Once you know you can never go back, I gotta take it on the other side.
Really? Mr. Originality.
So sign into your Fusion account, scroll over to the Design tab, and switch to Manufacturing. Open your data panel and pull up your Geneva Sprocket project that you worked on from the previous lecture. Your program should save automatically to the cloud. However, if you somehow lost your toolpaths from the previous lecture, don't worry, they are not mandatory for this class. If your toolpaths were not saved, make sure you go into the settings and check that your program is auto-saving. It is also a good habit to manually save your work prior to exiting Fusion. Now then, close your data panel to maximize your workspace. We will always start a job the same way, and that will be to create a new setup. Go to Setup and click on New Setup. This will bring up the stock offsets. The setup type will be milling. Here's where things get a little interesting. On the first side, the tolerances of our coordinate system was within the scope of our additional stock, allowing some small variances in its location, let's say 0.01 or 10 thousandths. On the second setup, we will need to be more meticulous in our setup so that both the bottom and the top line up. The tolerances assigned to this part will be plus or minus 0.001 or negative 1 thousandths. As engineers, you design the tolerances to your design based on the needs of the client, the design parameters, and pretty much everything you've learned in engineering school. Later in the quarter, I will cover some tolerancing so that you will have a better grasp on this concept. Machinists do not make the tolerances, but they are bound by them. That being said, to line up the two halves, we will need to choose a feature on the model that was already cut. We cannot use the edge finder this time because all of the reference edges are overlapped from an additional stock shown here. I modeled the vise as well as the first job and the parallels, so that you get a better idea of what you're working with when you go over to the machine. As you can see, the top left coordinate of our previous job is now the bottom right corner of this new setup. I can't use the top left corner this time because any variances are going to offset the two halves. The top right corner could get me closer because it's the same reference edge we used. However, any variances in the cut of the stock will also offset our coordinates. We only have one usable feature to use, and that's the center hole. When we set up the machines, we will use the dial indicator to find the center of the model. This is why on the bottom side we drilled and milled out the hole so that we could have an accurate feature to set up our coordinate system. This is also why you will want to plan out your steps prior to making any chips fly. Now let's work on our setup. Set your axes to X and Y axis. Once again, I need to find a feature on the model that specifies the coordinate system. In this case, the X is easy. I could just simply click on the edge of the gear splines. For the Y, flip over the model and select an edge that is perpendicular to your X. You can use most of these orientations to obtain the same results. For instance, click on the Z axis / plane and the X axis. For this option, I can click on a plane perpendicular to the desired Z axis, or an axis along the Z, and it will give me the same outcome. Then you just need to click on a perpendicular X axis. Flip the model over so that the top is facing you. Now you should notice that both the X and Y are facing the wrong direction. Z is facing towards you, which is correct, so you will need to click Flip X axis. Finally, we need to set the Z origin. You can see additional stock at the top of the model. Using the top of the model this time will not give us an accurate measurement because, once again, we want to use the model as a reference. Instead, we can use the parallels as the Z0 because it is touching the base of the model. I will show you on the second machine setup video how it is possible to obtain this zero. To set your Z at the base of the model, in the Origin pull-down menu, select Selected Point and click the bottom contour of the hole feature. As you can see, Z is zeroed at the base. Now click on your Stock tab, and under Mode, select Fixed Size Box. Measure the remainder of your material from the first operation. Remember that your X will be the longest measurement following the gear splines. Measure the Z from the bottom of this feature to the top of the stock. Plug all these values in and set your Z model position to offset from the bottom and type 0 in for its value. This is because there is no longer any remaining stock at the bottom of the model. Click OK to save the changes. Let's now set up the first operation, which will be the 2D face.
Whoa. 2D face, you say? I think I am way more qualified to discuss 2D face. When we discuss 3D faces, you can tell them all about that big of a nose. Alright, head over to my 2D realm and click on face. Not my face, that won't do it. Under tool selection, click on Mill Tools for Class. If there is no selection available, right-click on Local and import your tool library from either your file folder or our website. Select tool number 1, the 3/4 inch face mill. Your feeds and speeds have been set up for you, so click on the Geometry tab. Once again, you will notice that the entire project is outlined, notifying you of the constraints of the toolpath. Now this is all good, so click on the Next tab. If you set your heights as default in the last Fusion lecture, the first 3 should be clearance from retract at 200 thousandths, retract from feed at 200 thousandths, and feed height from top height at 200 thousandths. Set your top height at stock top and your bottom height at model top, and click OK. Your toolpath should now be rendered. Take a look at the red arrow. This is the start of your toolpath, and the green arrow is the end.
Okay, I will take this next one.
Go right ahead, Starshine.
I don't know what that means, but here we go. Click on 2D contour, select tool number 4, the 1/4 inch end mill from the Mill Tools for Class. Click on your Geometry tab and click on the contour of the gear. You can also click on the bottom contour because it follows the same path. Just make sure you understand your heights, which I will cover now. Click on your Heights tab and it will bring up your heights as well as a visual representation of your height offsets. Now let's talk about what these height offsets mean, starting with the top height and the bottom height. The top height is where you want the cut to start, and the bottom height is the final depth of the cut. I have my heights set up already the way I want them. Let's see what happens first running normally. You can see that the bottom of the end mill is set at 15 thousandths below the bottom of the gear feature, allowing enough clearance between the model and the vice jaws. I have now set my offset to -0.25 to show you what will happen if you set your depths too low. You can see that the cutting depth is well into the vice jaws, which is also known as a crash. On the program, I told Fusion that the vice jaws were part of the fixture. If the tool collides with the fixture, it will show up in red, indicating a crash. Let's go back and take a look at our height offsets. The feed height is the height at which the tool will rapid to before it transitions to its feed/plunge rate, which is the cutting velocity to enter the part. Somewhere in between your feed height and bottom height is where your lead in and lead outs are. Shown in our linking tab is the horizontal and vertical lead in and lead outs. As an example, I will exaggerate the lead in and lead outs and be able to show you on the toolpath. The tool will arc on both the XY plane and the Z plane, allowing you not only to cut vertically but also to ease the transition of the cutting tool, so it's not so dramatic.
Don't you mean traumatic?
I mean both. Most end mills are not designed to plunge straight down. Therefore, your lead-ins are important for vertically milling and decreasing the impact when the tool contacts the material.
It is important to note that if these values are too large and the feature is too small, the program won't generate a toolpath. So these values can be tweaked. However, they work well as their default, so leave them alone! Unless you have to change them.
Well, that's right. Now let's look at the retract height. This is the height at which the tool will retract before cutting the next path. The clearance height is the first height that the tool rapids to at the start of the toolpath, meaning it is only used at the beginning of the operation. These heights come in handy while watching the height offsets as the G-code is running. Your height should be set up by default. If not, look at mine and transfer them to your program. Set your top height to model top because we already moved the stock top. Set your bottom height to selection and select the bottom face of the Geneva sprocket. Let's set the offset to -0.015. If possible, you always want to cut slightly below your model.
All material, be it steel, aluminum, plastic, wood, etc., will leave burrs from the cut. Plastic is no exception. In fact, because of the flexibility of the material, you need to go even deeper. Plastic material has a tendency to be pushed out of the way as opposed to being cut. Moving on to the Passes tab, click on Multiple Depths. Change your maximum roughing step down to 0.1 and click on Use Even Step Downs. Then click OK. As you can see, now there are 3 layered cuts. The reason for this is because for this setup, full depth would be too aggressive. There are 2 reasons for this method. First off, when cutting a 2D contour, it does not take into account additional stock like adaptive clearing does. So you can see that the entire blade is engaged with the material as opposed to a percentage. This creates a lot of tool pressure and makes it difficult to extract chips. Get out of here, chips! The other reason is that the surface area being clamped in the vise is very small. If the force of the tool is greater than the shear force of the vise jaws against the material face, the part will kick out of the vise, allowing you to get more practice on the machine. We can minimize the tool pressure by minimizing the contact area of the end mill. Using even step downs simply makes each step even. The final depth of my cut is 0.235. I will choose a depth of 0.1. Instead of having a depth of 0.1, 0.1, and 0.035, the program automatically adjusts the Z level evenly.
For your next operation, click on 2D Pocket. You'll be using the same tool, tool number 4, the 1/4 inch end mill. Feeds and speeds are set up for you, so click on the Geometry tab. Click on one of the larger hole contours, now set your heights. You should know the drill by now. Being that this is your first use of the Pocket feature, your default heights will not be set, so take a moment to set them now to match mine. Set your clearance height from retract at 0.2, your retract height for feed height at 0.2, and the feed height from your top height at 0.2. Now set up your top height to model top and set your bottom height to selection. Select the bottom face of the Pocket and click your Passes tab. Like adaptive clearing, the Pocket operation is a roughing operation, so by default, stock to leave is already checked. We want to leave stock radially, but not axially, so change that value to 0 and click OK. Look at your toolpath and notice that the toolpath helicals in and then creates a long sweep. This is creating a lot of tool pressure at the end of the toolpath with 100% tool engagement shown here in the simulation. Let's make a change to this toolpath to minimize the tool engagement of the last step. Right-click on the 2D Pocket and click Edit. Head to your Linking tab and let's change the helical ramp diameter to 0.55 and click OK. This will enlarge your helix and remove material as it lowers. Alright, you little nightmare. You want to take this one?
Oh, I got this, Gonzo McPenny Pincher. Like my coworker just explained, 2D Pocket is a roughing operation, and we need to clean up the material we left behind. For that, we will use a 2D contour. Pull up the 2D contour menu. Select tool number 4, the 1/4 inch end mill. Go to Geometry and select one of the contours along the whole feature. Set up your heights next. Setting the top height to model top and the bottom height, click Selection. Click on the bottom feature of the hole and make sure no offset is selected. When you're satisfied with your heights, select OK to save the changes. Alright, let's wrap this thing up. The final step will be to clean up the edges using a 2D chamfer function. Under Tool Select, choose your tool number 5, the 1/4 inch chamfer mill. Under Geometry, select the sprocket contour, the top hole contour, and the bottom hole. Set your heights up per usual. Set your top height as model top, and this time we will select the bottom height as selected contours. This allows us to choose the 3 features with the 2 separate depths. Under the Passes tab, select the chamfer width to be 0.015 and click OK.
You are now ready to simulate the program. Now that you have both setups, you can simulate the entire program by right-clicking on the top setup, referred to as Setups, and click Simulate. Look for any crashes highlighted in red. After you are satisfied with the simulation, it is time to post your process. Once again, to post the process, scroll over to your second setup and click Post Process. Do not click on Setups, or that will copy both sides of your G-code to one post. Create a file name in the comment. Be sure that under your post configuration, it says Tormach Path Pilot Tormach 2 and post your project. If it does not say Tormach Path Pilot, you can find the post in the file folder you created for the class, or head back to the website and download it. Copy your post to your computer or on a flash drive for the machine, and that's it. Congratulations! You have a fully programmed completed part. Join us for the next Fusion video, where we'll show you how to set up a turning part to be cut on the CNC lathe.
You spin me right round, baby, right round, like a CNC spinning parts round, round.
Stop, they get it. We're working on a lathe. Just, those aren't even the words of the song.